Here I have the antenna structures connected to the network analyzer showing a bandwidth of about 30 MHz at 2.4 GHz. The coupling is around -60 dB. And my colleague moves the antenna, slight movements, from a distance such that his body doesn't interact with the antenna structure. And we see that small movements can change the coupling in the range of -30 to -60, -70 dB. And this is something we need to deal with. Here I have a closer look at the antenna structures, one horizontal, two vertical antennas, and the total area is about 7 cm by 8 cm. Here I have the same antenna structure, but this time is connected to LearTech platform, and we will be looking at different signals in real time in the baseband. The lowest signal shows the transmit power corresponding to the preamble sent from the first antenna, from the second antenna, followed by the preamble sent from both antennas at the same time to measure the equivalent channel, followed by several OFDM frames. And those spikes are the OFDM frames that are transmitted from the two transmitter antennas at the same time. This middle signal shows the received power corresponding to the first preamble, corresponding to the second preamble, and finally the effect of the cancellation in the air due to pre-equalization multiplication by the beam forming coefficient to cancel at the receiver antenna. And then on top we have the final cancellation. The top signal shows the effect of the final cancellation, which is the subtraction of the transmitted signal from the equivalent single input, single output channel that we have from the two transmit antenna to the receiver antenna. And we would like to study the effect of different environments in terms of reflection on the performance of the overall system, which is the combination of the cancellation in the air and final cancellation. To do this, my colleague is bringing a metallic plate close to the antenna to change the reflection, and as you see, the signals all fluctuate quite significantly in terms of the transmit power because the channel coefficients are changed, in terms of the received signal at the two antennas, which show that the coupling can be so quite significantly different. But the final algorithm, or the combination of all of this working together, is able to cancel the self-interference, and we have a very stable performance overall at the received. Here we have a patch antenna including the transmitter, receiver, and the auxiliary transmitter all merged together. Now my colleague brings a metallic ruler close to the antenna to change the coupling, and the lowest signal, which shows the transmit energy, the middle signal, which shows the effect of the cancellation due to the first algorithm, fluctuate quite significantly, but the top signal, which is the effect of the final cancellation in the baseband, has a stable performance.